The broadcast is now starting. All attendees are in listen-only mode.
Welcome everyone to the webinar release. Well, it's going to be a sort of a hands-on demonstration, and feel free to ask any questions during the webinar. We'll keep an eye on the question tab, and every now and then we'll look at it and answer them in between if you have any. So feel free to type any questions you have while we're going through the presentation. So to start off, I'm just going to give you a brief overview of what BOSpulse actually is. I looked at some people who are attending, and I'm not sure whether we all have familiar faces who already use BOSpulse on a regular basis. But I just want to highlight why BOSpulse is a good pulsation package from our perspective. And these points I'll also demonstrate while I'll give you the demonstration, and I'll also highlight the new features that are included in the new release. Well, easy model setup. It's fairly easy. There are a lot of different ways you can set up your model if you come from a Caesar package, or if you come from a isometrics, or whether you just want to model in BOSpulse alone. There's several different ways you can set up your model. All different methods are relatively easy to understand and intuitive, and they're also fairly fast. So that's the next point, our strong point in our opinion, that is fast and it's automated results and code checks. So there we try to minimize the user input and any steps necessary to generate sufficient output. We're trying to automate that so that the user only has to focus on what really matters, how to analyze the system, and not be involved with any computational stability or those type of things. But furthermore, we can do parameter studies. So it's relatively easy to set up a parameter study. You can run a lot of cases, and again, the post-processing is set up in a way that it's easy to view all that data. So you can generate a lot of data if you have a parameter study. We try to condense it to some useful data for an engineer to judge whether a system is okay or not. And then, if you have done your pulsation analysis, we also enable some coupling with some stress packages. So currently we're very strong with Caesar 2, so import output of model geometry, but also, of course, the forces that are calculated after the pulsation analysis. You can export those to Caesar 2. And actually, in a new release, we also include the interface with AutoPipe. So you can export forces in an AutoPipe format that you can directly use in AutoPipe for a dynamic mechanical simulation. And that's also something I will show later in the demonstration. And then finally, there's a continuous development. So this is one of our new releases. But we're continuously adding to the software, and I also wrote including our own. So we are also one of the main users of our own software package. It's really easy for an engineer, and I'm primarily an engineer doing consultancy projects in pulsation analysis. If there's something that takes me too much time, and I believe it can be automated, it's relatively easy for me to change the software focus to tackle those type of topics. And we actually have some of our customers, some of our more regular customers of the software, they give us similar input in optimizing their workflow. So yeah, if you're not convinced yet, stay tuned, look for the new release and see whether some of your issues have been tackled by them. So that was it about selling points or strong points of our software, and we'll just jump into the demonstration right now. So this demonstration is going to focus on highlighting some of the features of BOSpulse itself. It's not going to we're not going to build a very realistic system in some parts, and that's just because yeah, I just pull some stuff together and I'm going to show you different ways, and it doesn't always make sense. So the modeling is going to take probably 10 minutes. I'll take it a little bit slower to explain some of the steps we're doing, but I will show that in around 10 minutes you can set up a pulsation analysis with a complete code check for the API 618. So that already shows it can be relatively fast if you have the right information. So I've opened the model. I've given myself a little bit of a head start. So this is the passage of a compressor. So we have I can show you have 2 nodes, and on those 2 nodes we have a reciprocating compressor boundary condition. And I'll show you later what this the result is from this. But you can see one is the head end, so on the left side. So bear with me for 1 sec. I'll try to get a nicer view. Perhaps this is easier. So right now, to continue on, we have 2 nodes. The left is the head end, and on the right side we have a crank end. So this would be, you can view this as the cylinder, 1 cylinder of a compressor, and currently they're in the suction operating mode. So we're on the suction side. And this is only the cylinder passage. So we have to add some pulsation bottle on top of here and some connecting piping, etc. So before we continue, I'm just going to show you something we fairly often do before we start a simulation. We're going to set up, we're just going to look at what our boundary conditions look like. So we're going to add a long pipe boundary condition, or an anechoic boundary condition. So that means no reflections from this side. And this is useful. So we're not interested in acoustic resonance. We're just going to look at what our boundary conditions can do. So we've set it up. So this is a system we can run now. Before we do so, I would like to highlight we are conducting an API 618 analysis. We've already, this is some basic statistics. We have a 15 Hertz compressor right now. And then maybe interesting thing to highlight, for the fluid type, we're currently using an AGA8 natural gas. And this is something new in the new release. We've added this little bit of a tool. If you know the composition of your natural gas, you can fill in the molar volume, percentage volume of your gas, and you can it will automatically calculate all relevant properties. So it will calculate the viscosity, the density, the compressibility, and based on that, it will calculate the speed of sound. So this is a neat little feature we've added. Before that, you always had to calculate these, perhaps in an Excel sheet or some other tool you have lying around. But this definitely helps again in speeding up your analysis. So now we can simply run this system. We only have 1 scenario. It's a small system, so it's relatively fast. It's already done. And all I'm going to show is the flow rate at the different compressor boundary conditions. So here you can see a graph. You have the time on the horizontal axis, the flow rate on the vertical axis, and we see 2 colors. One is from the head end, and one is from the crank end. And here you can see, for example, the black one, which is the head end. There's a little bit of a higher flow rate, and the red one is the suction flow rate, or the crank end flow rate. And the crank end is a little bit of a smaller volume, a little bit of a higher clearance volume in this case, so therefore it has a little bit of lower flow throughput. So this all looks fine right now. We can say we set up our initial problem sufficiently well. So now let's continue on trying to make a little bit of a more realistic system. So there's several ways of of expanding your model, I'm just going to start with one, and that's simply creating new elements in BOSpulse itself. It's not per se the fastest, but it's still relatively easy to do so. So what we're going to do is we're going to connect this pipe, or that's maybe a little bit too long. Let's go for fun. We're going to connect our passage to a pulsation bottle. So this would be the entrance into the pulsation bottle. We'll add another element, and we'll make it in the horizontal direction, and we'll make it a little bit bigger. So this is going to be sort of a pulsation bottle. We're not going to do any very fancy pulsation bottle. So it's going to have no choke tubes right now, but just for illustration purposes. So we also go the other way. So right now we have our passages connected to a bottle. So let's add maybe one more element, and then we're going to exit our pulsation bottle from the top. That's maybe not the most intuitive configuration. And we're going to add, let's say, a 4-inch standard schedule. So I can just type 4 and an S, and we'll automatically calculate the correct outer diameter and the thickness, similar to perhaps Caesar. So, well, and then let's go make a turn to end off. So there we go. We have our pulsation bottle set up, and now there's some piping here. Typically what we experience, there are isometrics available or some model which we can model that up. So for this example, I'm gonna use the import, and I'm gonna import. Well, there are different ways of importing. You can import a CSO3 neutral file, a pipe profile, and I'm gonna import the piping component file. So this can be the electronic version of an isometric. And I have to make sure I want to extend my model. I do not want to replace my model. We believe this is a very useful function. We've modeled thousands of isometrics in a relatively short period of time using this new import feature. And then also even for creating a Caesar model, for example, you can go build it in BOSpulse or BOSfluids and then export it to Caesar2. So these are sort of the standard import options. It gives you some warnings, but that's okay for us right now. And here you can see the part we've imported. So it might not be, the diameter might be a little bit too big for this system, so it doesn't add up to the compressor system. But we're gonna, to continue on, we're gonna show you some features of how to manipulate your geometry. So for example, I do not want all these little branches here. So one thing I can do is I can simply select the line I want to keep, duplicate it, so now it's above here, and then I'm just going to select the line below it, and I'm going to delete it. So right now I only have a single straight pipeline. Yeah, so that's relatively fast and easy to do so. Now we perhaps want to rotate it, so we can go transform the elements. We can rotate it around the y-axis. So now it sort of matches up a little bit more with our system. And then lastly, we're going to connect this node to our compressor system. So we're going to look at this node 80. And we're going to add it to this element right here. And then we have our system connected. Okay, so perhaps we're not happy with the pipe schedule, which was initially in the PCF file. So what we're going to do is going to select all these elements. And we can simply all at once edit all their values, so we can make it a 4-inch standard schedule as well. So now it starts to look like a more typical piping model. All right, so Well, lastly, we need some kind of boundary condition here. So we'll say we come from some kind of vessel of 10 bar, a 10 bar G. So now we have a sufficiently detailed model to run it. So let's simply run it and take a look at the results again. Takes a little bit longer because it's a little bit longer, larger system. So let's look at the pulsations in this long line. If we double click, you can see blue lines are the pulsations in the line at the different frequencies, and the red line is your allowable. So right now we can see this system would be fine according to the API 618 for pulsation noise. And to continue on, we can look at the different harmonics, but then the easiest is to look at the API 16 pulsation compliance report. And here you can see the API check result in the past. But then if you continue on, you have to notice we didn't do any check for the compressor cylinder flange, no PSD, no pressure suppression device is highlighted. So we still need to do some work to make the API check fully work. Actually, before we go into setting up the API, I would like to show you some other things, or things BOSpulse can do. So let's make a copy and actually do a parameter sweep. So we created a new scenario, so you can add multiple scenarios, which is very useful if you have different loading conditions. You can easily distinguish between those, and we can make changes to only that scenario. So what we're going to do is, first of all, we're going to use a different solver. We're going to use a harmonic solver, which is a lot faster. So it's very useful to do large amount of parameter sweeps with the harmonic solver to get a good result or fast result for initial design. We're going to change the base frequency to a parameter. So we're going to call it frequency or freq. And all we need to do then is say we want 200 variations of that parameter. And we want to vary it between the 13 Hertz and 17 Hertz. So in this example, we'll change the frequency as a parameter, but you can also use the wave speed, pipe diameter, acoustic length of a pipe length. So there are a lot of different ways you can use that parameter sweep. But in this example, we'll do only the frequency. So we can simply run our model again. So right now it will take a little bit longer, but still only 3 seconds to compute 200 different calculations. And now if you look at the pulsations in this line, you can see that there's actually, we're exceeding, at some frequency, we're exceeding our allowable. So to clarify a little bit on this graph, again, the red line is our allowable. The blue lines are our pulsations at a certain frequency. So this would be our first harmonic. And because we vary our frequency, it will change a little bit around that 15 Hertz. And so our first harmonic is okay. Our second harmonic at some frequencies exceed our allowable. And so we continue on, and then at some higher frequencies, we also see that we do not conform to the API 618 pulsation allowable. Right, so this system would need some work to make it fully compliant. But first, there's another thing I should mention. It's a very neat feature. Before this feature was available, we had to, for every intersection with a bottle, we had to correct the branch length. So acoustically, this branch can resonate between the vessel wall or a little bit inside and the rest of the system. Geometrically, we model this branch from this band all the way to the center of the bottle. So there's a clear distinction between the geometric length of a branch and the acoustic length of a branch. So in the new release of BOSpulse, this is automatically taken into account. So it automatically corrects this branch length, even though geometrically it goes all the way to the center line. Effectively, from an acoustic perspective, it only goes into the vessel wall. So that, again, that leaves a lot of model setup work for an engineer is being automated. So again, saving time setting up a model. So now let's finally completely set up our API check. So what we need to do, well, let's go to the results first. What we saw when we go to the compliance report, that there was no compressor flange assigned, and there's no PSD assigned. So these two things we need to set up. So that's not an issue because it's relatively easy. We go to the compressor flange, which should be somewhere around here. And this is the cylinder, here's the pulsation bottle. And we're gonna just simply select compressor flange. And what this does, it doesn't change the function of the node. It only specifies that this is the node where we want to look at the pulsations for that specific API check. And we can either specify the pressure ratio or the compressor node. And our compressor node was 240. Yeah, so now it will look at this node below here, this node 240, and it will look at what is the pressure ratio at that node, and then it knows the allowable. It can calculate the allowable. So that was the first check. The second check was the PSD. So we can simply select the bottle, and we can change the element type to a PSD. And again, it doesn't change the function of the pipe element as much. It just allows the software to identify what kind of checks we need to do. So actually, let's take a brief moment. Did anyone ask any questions so far? No? Okay, then we'll just continue on. So now that the software knows that these elements are PSD elements, we still need to specify some additional things because for the PSD element, we need to calculate the shaking forces and check those against some allowable, and we also need to calculate the pressure drop over the PSD element. So we can go to analysis, we can go to PSDs, and we can add the PSD assessment right here. So we called our element, our identifier PSD1. Again, you can specify a compressor node or pressure ratio, so we'll do compressor node. Number of cylinders is 1. Axial stiffness is the minimum that's required by the API 618. This is something you can always check in the output, but this is something if you don't know too much about the system, this is a starting point. But you should always verify whether that's okay or not. Then we continue on. There's a moisture separator and checkbox. It will change the allowable a little bit. And then pressure drop we need to specify. So we can say we want the pressure drop from the compressor flange node, which was 15, to the outlet of our compressor, which was 50. Okay, so now it will look at the pressure at node 15 and 50, and it will calculate the pressure difference between those two. So then there's one last thing we need to do for the PSD element, and that's the custom force calculation. So I won't go too much into detail about calculation of forces, but yeah, you always need the unbalanced forces are generated by the changes in pressure at some surface at which the pressure acts. So in our PSD elements, it would be the heads on both sides. It's a simple bottle, so the difference in pressure between those heads in time will cause a shaking force. So what I just did while I was talking, you initially start with an empty field. You need to set the areas. So you set a node and you set an area, and it will look at the pressure at that node and multiply it with the area to generate or to calculate some unbalanced force in time. And this is done for customization purposes. Now you can, if you have different baffle plates, choke tubes, and you want to very accurately calculate the shaking forces, you can add each different baffle as a separate node with a separate area. And to speed up that process, because if you have a very complex model, it takes a lot of time to write out what the areas are of the different baffles of the different heads. We had a calculate areas button. This is new in this new release. and it will automatically calculate all the areas of all the nodes inside your bottle. So right now, it found 2 dead ends, sort of to speak. So that's potential areas where the forces can be generated, and those are just the 2 different heads. So this is a relatively simple bottle, so only 2 nodes. If you have more complex, it can add up to a lot of different nodes. But it definitely speeds up the process again. So now we're all done setting up the API analysis. We can rerun our simulation. So it will rerun the main case, which was just a single case, single frequency, and we'll also do the parameter sweep again. So now, if we go to the standard report, we can see the API check passed. This was not for a sweep, but for a single operating point of 15 Hertz. And now we can see there's a pressure drop calculation over the PSD. There's a pulsation check at the compressor flange, which is shown here. And there's an allowable shaking force check. And again, here's the axial stiffness is used to determine that allowable. And then the report continues on about maximum peak-to-peak pulsation levels in the piping itself. Again, you can look at the pulsations in the pipe by double-clicking on it, but we can also look at the shaking forces in the pipe, and those are relatively low. So continuing on the shaking forces, last thing I would like to show everyone is the new export function to Bentley AutoPipe. So you can go to Tools and Export Forces. So there are different ways of exporting it right now. You can go to Caesar2 data files, text data files, just a general format. But the new one is Bentley AutoPipe. And that's actually a very nice way it's written out, and you can directly import it in your AutoPipe model. The only thing you need to specify is the damping ratio. So let's take 3%, relatively standard. Frequency is 15, at which we want to analyze our system. And then there's a node remap. So in AutoPipe, doesn't specifically use the similar format as BOSpulse and Caesar2, so 10, 20, 30, but also use some identifiers. So if I wanted to, I could say node 60 in BOSpulse is node M16 in AutoPipe. And 70 is M70. If you don't do this, it will just take the BOSpulse nodes. And I think this might be a lot of work, but we're still optimizing it even further. But to give you a helping hand, you can save this table to a file and then import it later if you have a different model. So if you're sort of if you're smart about it, it can save you a lot of time as typing this once and then saving it to a file, and then you can reuse it for different runs. So in this example, let's only map 2 nodes, and let's do the first 3 harmonics. And here you can say the file name is force, so it will output it to the force.hmf. So we'll export it to this folder, which is empty. And then if we go look at the folder, we can see the file just being generated. And here you can see what's in the file. So this is directly usable for AutoPipe. What can you see here? We have 15 Hertz. We want to analyze the system at 3% damping ratio. These are our different nodes. We have a phase angle in this column. We have the forces in the X, Y, Z component. And then you can see most of the nodes are written out as the BOSpulse output, and then some is M70. And that's that node map we specified. And then continuing on, here's our second harmonic, 30 Hertz. Again, we have our nodes with forces. And then finally a third harmonic, 45 Hertz. And then we have our nodes with our forces and phase angles. So that was it for the demonstration. Feel free to still ask any questions or email us if you have any questions. If you enjoyed this webinar, and you're curious to hear more about upcoming releases of BOSpulse or other software, you can follow us on LinkedIn. That's the main channel we communicate these type of events. If you're interested in other webinars relating not only our software but engineering topics in general, you can also look those up on our website or on our LinkedIn webpage. So thank you very much, and let's see whether there are any questions. So no questions at this moment. We'll stay alive for another 5 minutes, but I would say this is the end of the webinar. So thank you all for joining, and perhaps see you next time.